Nothing so far. Right, then the next part that we are going to have a look at is special machines. And this is what we're going to do. The question. Okay. Today we're going to look at self-starting methods of a single-phase induction motor. So first of all, you've got a split-phase resistance start motor. Then you can just look at it. That's the way that it's working. We've got an auxiliary winding and a main winding. Then with a centrifugal switch. And as the motor reaches a certain speed, that one opens and the auxiliary winding is cut out and it only runs on the main winding. Now, these two are supposed to give you, if we look at that main winding and the auxiliary winding, will give you a phase shift close to 90 degrees. So that's all that's needed for this motor to start, is that phase shift. And once it started, the auxiliary winding is cut out. Okay? Then we've got a split phase capacitor motor. Okay. And there we have a permanent split, single cap. So here we've got the two windings, start auxiliary windings and a main winding. So the one main auxiliary winding is cut out. After a certain speed, this thing opens and it runs on those two. Now, before this one, the auxiliary winding is made of thin wire. It's not that thick because it's only in the circuit for a few seconds. Here, this one is also made of a bit thicker wire because that is permanently in the circuit. And then you can read all about that in the book. And then we have a two-value capacitor. Also just to give you better starting torque. And then after a while, as this motor reaches a certain speed, close to synchronous, to a running speed, and that one opens and it runs like that. Now, we get to the problems. It says there, the main winding of a single phase is connected to a power supply. The power factor was 0.4. The impedance of the auxiliary winding was 32 angle 40. Determine the value of the cap that would give 90 degrees phase shift. Now, right, for the main winding, phi will be r cos of 0.4. That gives us a value of 66.4 degrees. Right, so let's look at a phasor diagram. There's our voltage, and the main winding has got an angle there of 66 degrees, 0.4. The auxiliary winding, like I said, was 32 with an angle of 40. Now, what this cap does, it moves this one, let's say, that's the current in the auxiliary, and after the cap moved it to that position, so that this angle here now becomes 90 degrees. Then I'm sorry. Okay. So the degree alpha is then 90 degrees minus phi over main. So in other words, that's 90 minus 66,4. That means it's 23,6 degrees. So now, if we look at the auxiliary only, that was 32 minus 40. And now it must become the 23.6. So what the cap does, it supplies all of this reactive power. So let's call this A and B. Now, if we look at this value here, if you break it up into its two components, 40 at an angle, or what was it, 32, or 32 angle 40. Just break it up into the rectangular form. Then we get that value and that value. So let's see. This one becomes 24,513 plus J 20,5. And now we want this value. And we've got this is 24,513. Eh? So if we use trigonometry, the tan of 23,6 is that one, let's say that's BO or OB over 24,513. So OB is going to be 24,513 tan 23,6. And the sum of those two, that gives us 31. How much is that? And OA is 20,5, 6. And that one, let me check quickly. $10.71. So therefore, AB is the sum of the two,